Hello everybody, welcome into another lesson. So today we are going to talk about lines in space. Now, dealing with equations of lines in space is very different from dealing with them in the 2D plane, because you don't have a normal slope to deal with. Yes, you can find the slope of a line in space, but it's not the same because you also have the z-coordinate to consider. Where before, when we were dealing with equations of lines, we only had the variables x and y, but in space we have the variable z we also have to consider. A lot of problems for finding the equation of a line in space are going to read something like find the equation of the line through point P parallel to vector v. So you'll have some point P that the line runs through with coordinates x1, y1, z1 parallel to vector v, so that vector v would have a, b, and c for your various components. Those are also called your direction numbers. Well, if you have a vector parallel to a vector, that means it's just a scalar multiple of that vector. We tend to call that t times vector v, that scalar multiple being t. So it's going to be the same vector just multiplied by a scalar. So it would be t times this vector v for being parallel to vector v. And then when you go to find the equation of lines in space, you're going to have parametric equations, which you can always find. And then there are symmetric equations, which sometimes you can find, sometimes you can't. There will be a case you can't find symmetric equations if you have a direction number or a component of vector v that equals 0. In order for a symmetric equation to work, you actually have to have a non-zero direction number, which we'll get into in a minute. But to find the parametric equation of a vector, parametric equations, I should say, of a line rather, it's going to be x equals this x sub 1 plus that direction number a times t. If you distribute that t through your vector, it would be a times t for your x component. So if you had 0 for t, it'd be 0 times a, x would equal that x1, and then for any subsequent values of t, it's just going to be multiples of that direction number a, so you'll get different x coordinates, so you can plot a line. And then y would equal y sub 1 plus b times t, and then z would equal z sub 1 plus zt, or ct, excuse me. So those are your parametric equations. Now, to get symmetric equations, for each variable you're going to solve for t. And as true, t always equals t. Any day of the week, t is going to equal t. So if you take each of these values for t with the corresponding variables, you would get x minus x sub 1 divided by a equals y minus y sub 1 divided by b equals z minus z sub 1 divided by c. That they're all equal to each other. This is where you see that you have to have a non-zero direction number because you would be dividing by 0. So that's why it may not always be possible to find symmetric equations, but you can always find parametric equations. But we're going to do a few examples where we're given, first we're going to start out, it's going to be the equation of the line through point P parallel to vector v, and then for the later exercises, we're going to have to find the equation of the line going through 2 points and get that direction vector and all that. So we'll go ahead and get started. All right, so in this case, they take it easy on you. point P is at the origin. We'll start right at the origin for point P. So P is at 0, 0, 0. Vector V is going to be 1, 2, 3. So vector V is 1, 2, 3. So they actually made this one pretty easy. So we're going to find the equation of the line through point P, which is at the origin, parallel to vector V with direction numbers 1, 2, 3. If it's parallel to vector V, that means it's going to be the same vector multiplied by a scalar. In this case, we call that scalar t. So t times vector V would be t times that vector 1, 2, 3. Now we can easily start finding the parametric equations. If we want to look for the parametric equations, we're just going to we're going to say x equals our x sub 1, which is 0. Well, 0 plus anything is at anything. So 0 plus that 1 times t, or just simply 1t or t. So x equals t. Y would equal that y in the point P, which is 0 plus 2 times t, or simply 2t. And then z is going to equal that 0 from point P plus 3 times t, or simply 3t. So your parametric equations end up being x equals t, y equals 2t, z equals 3t. Now in this case, all of our direction numbers are non-zero numbers, so we can find symmetric equations. All you're going to have to do is take each of these variables, solve for t, take each of these parametric equations and solve for t. Well, if t equals x, you'll literally just get x would equal, and then t would equal y over 2, so x equals y over 2, which is going to equal then, if z equals 3t, this would mean t equals z over 3. So your symmetric equations would be x equals y over 2 equals z over 3. Those would be your symmetric equations when you solve for t from each of those parametric. And why don't we draw the line? So we have this point P at 0, 0, 0. Let me draw in a different color here. So here's point P at 0, 0, 0. And then if it goes 1, 2, 3, that means we're going to go 1 in the x direction. See, 1 in the x, 2 in the y, and then up 3. So that would be the next point, and if we keep doing that, the line's going to go like this in space. And we could extend this down further, and there is your line in space, using the vector to get your subsequent points. So that is how you would graph a line in space. Alright, and I got more. Alright, there we go. Redrew the axis. So let's do another one here. Alright, so this time point P is at 3, negative 5, 1. Our direction vector, vector V, is at 3, negative 7, negative 10. So we have point P that the line goes through is at 3, negative 5, 1, the direction vector, vector v, is at 3, -7, -10. Well, again, if the line is parallel to vector v, it's just going to be that scalar multiple of t times vector v. So we'll take t times that vector of 3, -7, -10. Now from here we can easily find the parametric equation. X would equal that first x coordinate of 3 plus that 3 times t. Y is going to equal that -5 coordinate plus that -7t, or -5 minus 7t. And then z is going to equal that 1 plus the -10 times t, or minus 10t. So for parametric equations, you get x equals 3 plus 3t, y equals -5 minus 7t, and z equals 1 minus 10t. Those are the parametric equations of the line. Now, next thing we want to do is find symmetric equations. And we can do that because all of our direction numbers are non-zero numbers. So if we solve for t for the x variable, you would end up getting 3t equals x minus 3, which would have to mean that t equals x minus 3 over 3. If you do it for y, you would get that -7t is equal to y plus 5, which would give you that t equals y plus 5 over -7. Then do it for your z, you would end up getting that -10t equals z minus 1, which would turn into t equals z minus 1 over -10. So for your symmetric equations, you'll end up getting then x minus 3 over 3 is equal to y plus 5 over -7, which is going to equal z minus 1 over -10. Those would be your symmetric equations of the line. And this is actually proper form when doing symmetric equations. It's okay to have a negative in the denominator. That does happen with symmetric equations. So don't be alarmed by that. Alright. So these are where the vectors were given to you. I'm going to change it a little bit, where this time you're given parametric equations of a line. But it's not as bad as you think. Sometimes they won't give you the vector outright. They'll give you parametric equations for the line that it's parallel to. Let me rewrite this. So we're going to find the equation of the line through point P parallel to the line x equals 5 plus 2t, y equals 7 minus 3t, and then z equals negative 7. Am I reading that right? Whoops, wrong line. Negative 2 plus t, excuse me. Where point P is located at 2, negative 3, 5. Alright, so we're going to find the equation of the line through point P parallel to the line x equals 5 plus 2t, y equals 7 minus 3t, z equals negative 2 plus t. And point P is at 2, negative 3, 5. Alright, so they don't give you the vector that it's parallel to outright, but we got the next best thing. You want to know why? Because this line has parametric equations. And in parametric equations, that coefficient of the t are always your direction numbers from the vector. So we actually got the next best thing. We can say this vector t times v, which we have right here for our direction numbers. You don't even care what the constant terms are. Just look at your coefficients on the t. This would be t times 2, negative 3, and 1, based on the coefficients of your t for each of these parametric equations. So we actually got the next best thing. So if you're given the parametric equations of the line that it's parallel to, ignore your constant terms for each of these parametric equations. Just look at your coefficients on the t. Those give you your direction numbers. Now we can proceed to find the parametric and symmetric equations of this line. So parametric, that's pretty easy. So x is going to equal that x coordinate of 2 on point P plus 2 times t. Y would equal negative 3 minus 3t. And then z is going to equal 5 plus t. So there are your parametric equations. Excuse me a second. Alright, so now we can find symmetric equations because this vector has all non-zero direction numbers. So let's go ahead and solve for t for each of these. If you do it for the x variable, you'll get that 2t equals x minus 2, which would give you that t equals x minus 2 over 2. Do it for your y, you'll end up getting negative 3t equals y plus 3, which would give you t equals y plus 3 divided by negative 3. And then you have, if you do it for z, you'll just end up getting that t equals z minus 5, which we should really say over 1 if we're doing symmetric equations. We should do that over 1. So the final answer for your symmetric equations, you'll get x minus 2 over 2 equals y plus 3 over negative 3 equals z minus 5 over 1. Those would be your symmetric equations for this line. So if you're given parametric equations, you really got the next best thing to getting the vector. And we'll do one more like this, then we're going to do several exercises where we're only given 2 points instead. Alright, so we're going to change these equations here. I'll keep the general format, but we're doing a very similar exercise. Let's just erase all this down here. Alright, so we're going to find the equation of the line through point P parallel to the line, again in parametric equations. This one is 3 plus 3t. Y is 5 minus 2t. Z is negative 7 plus t. Point P itself is at 1, 0, 1. Alright, so what this is really going to be is find the equation of the line through point P, which is at 1, 0, 1, parallel to the line with parametric equations x equals 3 plus 3t, y equals 5 minus 2t, z equals negative 7 plus t. Well, again, if you're given parametric equations, just ignore your constant terms. Don't even care about those. Look at your coefficients on your t variables. Those are your direction numbers for your vector. So if you take t times that vector v, you'll end up getting t times, then you got 3 on the x coefficient for the x variable. You got negative 2 on the y variable, and then you got 1 on the z. So there's your direction numbers. You got 3, negative 2, 1. Now we can go ahead and find the parametric equations. So x would equal that x coordinate of 1 plus that 3 times t, so x equals 1 plus 3t. Y would equal that 0 plus negative 2t, or just simply negative 2t. Z is going to equal that 1 plus 1t, or simply 1 plus t. So those are your parametric equations for this line. And since our direction numbers are all non-zero, we can actually now find symmetric equations. It won't be hard to do at all. So let's solve for t for each of these variables. If you have x equals 1 plus 3t, that means 3t equals x minus 1, which then means t would equal x minus 1 over 3. Do it for y. If y equals negative 2t, well, that would just give you that t equals y over negative 2. And then if you do it for z, you would end up getting t equals z minus 1 over 1. So the final answer would end up then being x minus 1 over 3 equals y over negative 2 equals z minus 1 over 1. Those would be your symmetric equations for that line. Alright, so far they've given you a point and either the vector it's parallel to or the next best thing with the parametric equations that the line's parallel to. Now we got to find the equation of a line through 2 points in space. So let's do that. Alright, so we're going to find the equation of the line through points P and Q, where in this case P is 2, 0, 2, Q is at 1, 4, negative 3. Alright, so P is at 2, 0, 2, Q is at 1, 4, negative 3. Now, believe it or not, it's not all that much different than what we've been doing. The biggest difference is we have to find the vector, the direction numbers. So, the line's going through those points, so we need to find a vector. So, let's find vector PQ to start with. So 1 minus 2, that's negative 1. 4 minus 0 is 4. And then negative 3 minus 2 is negative 5. Okay, now we got our vector, which are going to be our direction numbers. Now what I need to say about when you have an equation such as this, when you're trying to find the equation of a line through 2 points, the symmetric and parametric equations are not unique. What does that mean? That means you could pick any point on the line plus your direction numbers times t. So you may get different results. If we pick point P, so let's go ahead and do our parametric equations. You pick point P, that's your initial point, right? You would end up having x equals 2 plus negative 1 times t, or 2 minus t. Y would equal 0 plus 4t, or simply 4t. And then z would equal 2 plus negative 5t, or 2 minus 5t. That's assuming you pick point P for your initial point. Now, a line goes through those points, right? This isn't just a line segment that connects the points. It goes through those points. So there are infinitely many points for the line. What stays the same is your vector. That's consistent through the entire line. So it really doesn't matter what point you pick on the line. What matters is you keep the same direction numbers for the variable component of your parametric equations. So what if we pick point Q? We can pick point Q. So x would equal 1 plus negative 1t, or 1 minus t. Y would equal 4 plus 4t. And then z would equal negative 3 minus 5t. So in either case, notice one thing that is consistent between both sets of parametric equations. The coefficients on your t are the exact same. That's because those are your direction numbers. It's just your constants correspond to which point you started with. Both of these would be correct, and there's actually infinitely many possibilities depending upon which points you pick. But traditionally people use point P, but sometimes you may use point Q. It's really your preference, and if you're working out of a textbook and you're going to check the answer key, you may see a completely different answer from point P. It may be based off of point Q, and you may think you got the answer wrong when you didn't. So that's why I wanted to reiterate that your parametric equations, and of course the resulting symmetric equations from those, are not unique. So bear that in mind. Now, we can find symmetric equations then by solving for t. So if we do it for x, you would end up getting negative t equals x minus 2, which would give you that t equals x minus 2 over negative 1. Do it on y, 4t equals y, so t would just equal y over 4. Do it for z, you would end up getting negative 5t equals z minus 2. So t equals z minus 2 over negative 5. So your symmetric equations are going to be x minus 2 over negative 1 equals y over 4 equals z minus 2 over negative 5. Okay, so those are your symmetric equations. And had we used the point Q1, your denominators would have stayed the same because those are your direction numbers. What would have changed was your numerator with the x, y, with the constant terms in the numerator. So again, parametric and symmetric equations are not unique. There are many different possibilities. Okay, let's do one more of these. As you see, it's really not as bad as it looks. So let's get a point P and a point Q. We're going to find the equation through two more points here. The equation of a line through 2 points. So point P is going to be negative 3, 8, 15. Point Q is going to be at 1, negative 2, 16. So we want to find the equation of the line through points P and Q with point P at negative 3, 8, 15, Q at 1, negative 2, 16. Well, we definitely got to find a vector in order to have a chance of finding the equations of the lines, right? So let's find vector PQ. So if I take 1 minus negative 3, that turns into 1 plus 3, which is 4. Negative 2 minus 8, that's negative 10. And then 16 minus 15 is 1. So now I got my direction numbers from vector PQ being 4, negative 10, and 1. So now we can find parametric equations. Let's just stick with point P. I personally like to use point P. But again, it's your preference. You can use point Q and still get a correct answer, so long as your direction numbers are the same in the equations. So x would equal, then from point P, I'll take the x coordinate of negative 3 plus 4 times t. So negative 3 plus 4t, that's what x would equal. Y is going to equal then that 8 plus negative 10t, so 8 minus 10t. And then z is going to equal that 15 plus 1t, or just 15 plus t. So I get my parametric equations being negative 3 plus 4t, 8 minus 10t for y, and then 15 plus t for z. Now we can find symmetric equations if we solve for t for each of these variables, for each of these equations. So you would get 4t equals x plus 3. So then t would equal x plus 3 over 4. And then we do it for y, you would get negative 10t equals y minus 8. So then t would equal y minus 8 over negative 10. Then do it for z, you would get t equals z minus 15. But we should really put that divided by 1 since it's a symmetric equation. So now we got our symmetric equations since we solve for t. So we got x plus 3 over 4 equals y minus 8 over negative 10, which equals z minus 15 over 1. And there are your symmetric equations. Alright, so that's it for this lesson. We only have 2 more lessons left in the course. So the next lesson is going to be about planes in space. We will actually get into finding equations of planes and graphing planes. And even finding the line of intersection between 2 planes. So I hope everybody has a great day. Take care.